In this video here, we're going to take a look at divisibility tests. Now, you're probably already familiar with how to determine whether an integer is divisible by 2, or 5, or 10. And we also have similar rules to determine divisibility by 3, 4, 6, 9, and 11. Now, we can also go on to prove these divisibility tests by using modular arithmetic. And to do this, we need to write the number as a sum of its digits multiplied by powers of 10. So a number n with decimal digits an minus 1, an minus 2, so on and so on, can be written as follows. So we get the following here, right? So I get 10 to the n times an plus 10 to the n minus 1 times an minus 1 plus 10 to the n minus 2 times an minus 2 plus so on and so on, all the way up to 10 times a1 plus a0. So if we have a 3-digit number, n equals 3. If we have a 5-digit number, n equals 5. And for example then, we can write 4,318 as 1,000 times 4 plus 100 times 3 plus 10 times 1 plus 8. So in this case here, right, this number is a 4-digit number, so n equals 4. And hopefully then, this concept here is pretty straightforward. So to get us started here then, let's just quickly go through the divisibility rules. So to finish with here then, let's just quickly run through all of the different divisibility rules here. So an integer is divisible by 2 if and only if the last digit is even. So hopefully, nice and straightforward and a rule that you're already familiar with. For 3 then, this is if and only if the sum of its digits is divisible by 3. For 4 here, this is if and only if its last 2 digits are divisible by 4. For 5, this is if and only if the last digit is 0 or 5. So hopefully, again, similar to 2 here, this is a rule that you're already familiar with. For 6, this is if and only if it's divisible by both 2 and 3. For 9 here, this is if and only if the sum of its digits is divisible by 9. So very similar then, similar to divisibility by 3 here. For divisibility by 10 then, this is if and only if its last digit is 0. So again, similar to 5 and 2 here, hopefully a rule that you're already familiar with. And then finally to finish with here, for 11, this is if and only if the difference between the sum of its digits with even position and the sum of its digits with odd position is divisible by 11. Okay? So all of these rules here are the divisibility rules that you do need to be familiar with, right? So just make sure then that you do learn all of these different rules here. Most of these are pretty easy to remember, right? Probably the most challenging is 11, okay? And even that is pretty straightforward, and you'll see that very shortly as we work through a practice question, okay? So there we have it then. That concludes this introduction here to divisibility tests. So what we're going to do then is just work through 2 practice questions on divisibility tests. So let's just get started then with question 1 here. So let's just get started here then with question 1. So for question 1 then, all we want to do here is use the divisibility rules to determine the following. So for the first part of this question here, part A, we've got this number, 32,748. We want to check then whether this is divisible by 4. Okay? Now don't forget then, for divisibility by 4 here, nice and straightforward, all we need to check then is whether the last 2 digits are divisible by 4. Well, in that case then, 48 here is equal to 4 times 12. Okay? So what that tells us then is 4 divides 48, and therefore then, so let me just write this here, so 4 divides 48, and therefore because 4 divides the last 2 digits of the full number here, what that tells us then is 4 divides the full number, so 32,748. And there we have it, so nice and easy, that gives us the solution to part A. Now for part B then, what do we have here? So we're checking whether 8,142 is divisible by 6. So for divisibility by 6 here, it needs to be divisible by both 2 and 3. Okay? Well, this number here, straight away I can see that it's even. So 8,142 is even. So therefore, divisible by 2. divisible by 2. And now for divisibility by 3 here. It always trips me up. And now for divisibility by 3 here, all we need to do then is add the digits together. So 8 plus 1 plus 4 plus 2. So what does that give us here then? So 10, 11, 15. Well, does 3 divide 15? Well, yeah, 3 divides 15, right? So let me just make a note here. 3 divides 15, and therefore then divisible by 3. So divisible by 3. And in that case then, because it's divisible by both 2 and 3 here, in that case then, this number here, 8,142, is divisible by 6. So 8,142 is divisible by 6. Okay? And there we have it then. So that gives us the solution to part B. And then finally here we have part C. So for part C, then we're checking whether this number here is divisible by 11. So for divisibility by 11 then, so for divisibility by 11 here, what we do then is we take the first digit as positive, the next digit as negative, positive, negative, positive, negative, add those together. Okay? So I've got 5 minus 3 plus 9 minus 4 plus 2 minus 7. Okay? And if we evaluate this here then, what does that give us? So if you evaluate this here then, that's 2, 11, 7. They cancel, I just get left with 2. So this here then is equal to 2. So does 11 divide 2 here? Okay. So does 11 divide 2? Well, clearly not, right? So 11 does not divide 2. And therefore, in that case, then 11 does not divide this number here. So 11 does not divide this number here. So 539,427 there. Okay. And there we have it then. So that gives us the solution to part C and the solution to question 1. And then finally, to finish with here, let's just have a go now at the very last question, question 2. So for question 2 here, what we have then is n, which is a 3-digit number, ABC, so that n is equal to 100a plus 10b plus c, where a, b, and c belong to the following set, and a is not equal to 0. So for this question here, then we want to prove that 9 divides n if and only if 9 divides a plus b plus c. Okay? So this rule here, this is our rule then for divisibility by 9, right? And we can prove this result then by using modular arithmetic. So to get us started here then, let's just consider what happens with 110 mod 9, right? What are they congruent to? So 100 here is congruent to 1 mod 9. So 100 is congruent to 1 mod 9, and the same is true here for 10. Okay, so 10 is also congruent to 1 mod 9. Okay, and why is that important then? Well, what that means here is we can rewrite n. So therefore n is equal to, so originally we had 100a plus 10b plus c. So 100a plus 10b plus c. Okay, but this is congruent to, well, 100a, well, 100 is congruent to 1 mod 9, so that's just a. The same is true here for b, so 10 is congruent to 1 mod 9, so that's a plus b plus c. Okay, mod 9 here. Like so. Now, if n here, okay, or if 9 divides n, then n must be congruent to 0 mod 9. Okay, so let's just make a note here. So if n is congruent to 0 mod 9, then what we require here is, so let me just write here, if and only if. So n is congruent to 0 mod 9 if and only if a plus b plus c is also congruent to 0 mod 9. Okay? So a plus b plus c is congruent to 0 mod 9. Okay? And therefore, in that case, then, what we can say here is 9 divides n if and only if. So if and only if 9 divides a plus b plus c. Okay? Exactly as we wanted to prove here. Okay? So there we have it then. Hopefully not too challenging there. And as you can see, you can also use, this concept here of what we've just done right for divisibility by 9 to also prove the other divisibility results. Okay? So there we have it then. That gives us the solution to the very last question, question 2. And that brings us to the end then of this video here on divisibility tests.